Well, hello again and welcome to our journey into complex analysis, and we've been looking at evaluating real improper integrals using complex analysis methods. We can also evaluate real trigonometric integrals also using complex analysis in a very nice way. So in particular we're going to be looking at integrals of this form where we've got a function of coses and sines and we're integrating from 0 to 2 pi. Sometimes if the integral's from 0 to pi, you can use symmetry and then go from 0 to 2 pi and halve it if you've got some symmetry going on. The f of s of t is a rational function of s and t, and that can be evaluated making a complex change of variable z equals e to the I theta, and that's all you need to do. You just put z equals e to the I theta and turn it into a complex contour integral. So as theta goes from 0 to 2 pi, z is going to zip once around the unit circle, centered the origin. And so such a change of variable converts the integral into a complex contour integral, with the contour, as I mentioned, being the unit circle. So I'll do a couple of worked examples of these. The first one is the integral of d theta over a plus cos theta, where a is a number which is bigger than 1. We need a bigger than 1, otherwise this will be an improper integral. So this is doing a whole family of integrals. Here's the worked solution to this. So there is the integral, and all you do is, that's almost magic, you put z equals e to the I theta in. Now we have to replace the d theta element, so we differentiate with respect to theta. You get I e to the I theta, which is just I z. And we're going to need to convert cos theta, so we recall that cos theta is e to the I theta plus e to the minus I theta on 2, which is z plus 1 over z over 2. So we can now convert this real integral along the real axis to a contour integral around the unit circle. So as theta goes 0 to 2 pi, z's going around the unit circle. So we just plug everything in, and we get dz over iz. That's from the dz, the theta is I z above, and we replace the cos z with z plus 1 over z. At this stage we tidy up all the double-decker fractions. I can double top and bottom. There's a 1 over I may as well take out the front, and when you rearrange you get this quadratic in the bottom. Now the function then f of z squared plus 1 over z, plus 2z plus 1, you can find the singularities of this by simply, I should say 1 over this might be better to write. So f of z is 1 over this, has singularities in the unit circle. Remember, we're only interested in being in the unit circle when the denominator is equal to 0. And I can complete the square on this, which is the easiest way of dealing with it, and I can solve and I get these two values for z. Now you need to convince yourself that one of these, the minus a minus root a squared minus 1, will be outside of the unit circle, whereas the minus a plus root a squared minus 1 is inside the unit circle. One way of seeing that is to rationalize the numerator here by multiplying by conjugates, and then you can see that the modulus of z will be inside the unit circle if I take the positive sign, and outside if I take the negative sign. So inside the unit circle, that's our singularity, and I'll just give that a name and call it alpha as usual. We can get the residue then. It's a simple pole. So the residue is just of f is just the limit as z goes to alpha, of z minus alpha times the function f, which is this. Again, you let L'Hopital do all the work, so you just differentiate the top, differentiate the bottom, you get 2z plus 2a, you put z equals, 2z plus 2a, you put z as alpha, you get 2 alpha plus 2a. Now alpha, of course, was back here, so if you double this, the 2a's cancel and the minus 2a, and I just get twice the square root here. And that's it. There's no bounding argument to worry about. We just plug this straight back in. So the integral that we started with then, up here, the integral I is then just 2 over I 2 pi I times the residue, and that simplifies to 2 pi on root a squared minus 1. You see again why we required a to be bigger than 1 for this to make sense. So that's a very nice application of these of complex analysis to these trig integrals. As a second example, we're going to work through the slightly more sophisticated integral. The integral from 0 to 2 pi cos 3 theta on 5 minus 4 cos theta. Now, very interesting as we work through this one, interesting thing happens with this. Here's the worked solution to it. So there's our integral. And you don't need to do this first step, but if you don't do it, it will make the algebra and the analysis much more complicated. So you write cos 3 theta as the real part of e to the 3i theta. As I said, you don't have to do this. You can do it without doing this. And what you'll end up with, I'll invite you to check through and check the details, but if you don't make this step here, then you will end up having a pole of order 3 at z is 0. I'll leave you to check that, and it's pretty horrible to get the residue out. What we're essentially doing, I'm really just going to add in I times the integral 0 to 2 pi of I times sine 3 theta over 5 minus 4 cos theta. And as we'll see, that integral turns out to be 0 anyway. And so by adding in nothing, some rather strange philosophy going on here, by adding in nothing and looking at this, we actually get rid of a pole of order 3. That's more philosophy than mathematics, but that's an interesting exercise. I invite you to do this without converting it to exponentials, and you'll find the calculations are much more complicated. Anyway, enough of that. So we do the usual thing. We put z as e to the I theta, so dz is iz. The cos theta is z plus 1 on z over 2. And I can substitute that all in now, so I get the real part of mod z equals 1. So as theta goes 0 to 2 pi, then this whizzes around the unit circle once. Our e to the 3i theta now becomes z cubed times our d theta is 1 over iz dz. In the denominator we have 5 minus, we had a 4 over 2, so the 2's cancel and I get that. Again, we clear the double-decker fractions. I'm going to multiply top and bottom by z, and I take the 1 over I out. I'll get a z cubed on the top, and I'll get 5z minus 2z squared minus 2 in the denominator. So again, I'm going to take this function here, and this is going to have singularities in the unit circle when this quadratic, I've just multiplied by minus 1, when this quadratic is 0. This quadratic happens to factor nicely, so we just get 2z minus 1 times z minus 2 is 0. And so the singularities will be at z equals a half from the first bracket. Z equals 2 doesn't interest us because it's outside of the unit circle. So we just get z as a half. Again, it's going to be a simple pole. So the residue is going to be just the limit. You multiply by z minus a half times the function. Again, let L'Hopital do all the work for you. This is not a 0 at a half, so you whack it in. You get a half cubed. Apply L'Hopital to what's left. Differentiate that, you get 1. Differentiate that, you get 5 minus 4z, and you replace z with a half. And when the dust settles on all that, you just get 1 on 24. So the integral we're looking for then is the real part of, we had the 1 over I back from over here. You've got 2 pi I times the residue, and we just get, now by the way, that is in fact real, so you don't need to take the real part, it is already real. So you get pi on 12 as the value of the integral. That also tells me that the corresponding sine integral must be 0, because the sine integral would be the coefficient of I in this expression, but in fact it is in fact real. And so this is what I said before. this integral is 0. Now, by the way, you can evaluate these integrals using the t formula but again, I invite you to try that. The analysis of doing that is very complicated. You can try doing this using the t substitution, t equals tan a half theta, but it's going to be pretty horrible with that cos 3 theta to worry about. So there's a nice application of the complex analysis to these trig integrals. There's a little challenge problem here. We've got the integral from 0 to pi, and we've got a over a squared plus sine squared theta. That makes it a bit more complicated. And note, this is going from 0 to pi. So as a first step, you would turn this into an integral from 0 to 2 pi, and using the symmetry of the sine squared, you can just put a half out the front. And then I invite you to fight your way through this, and that's the answer you should get at the end, and see if you can do that using complex analysis methods. That's the end of this little section.